So on your little practice sheet, let's draw a Bohr model atom of sulfur. And I should point out, this is technically really all wrong. What do I mean? Well, see how big I've made the nucleus this big? Remember the video that we saw? We said if the nucleus was the size of a marble, the atom would be the size of a football stadium. I've made the nucleus bigger than a model. The electron shells should probably be like on the edge of Pitt Meadows somewhere. We can't draw it like that. So first of all, Brady, I want you to realize the scale here, all garbage, okay? Secondly, this is a model. Atoms don't really look like this, even if you zoom in. We're going to draw electrons as little dots. They're not. They're very, very complicated sort of clouds of charge. Well, we can't draw that very easily. But you know what? This model, Franz, will explain an awful lot, even though it's mostly wrong. And that's why you're always going to hear me call it the Bohr model. You're not going to hear me actually say, this is what, if you could zoom in on the fundamental level, this is what you would see. Okay? Let me erase that scribbling there. So if we were drawing sulfur, a Bohr model of a sulfur atom, first thing I would do is I would find sulfur. Found it? Element number what? What does that tell me? Okay, in the middle of the nucleus, I would write here 16 protons. Now, in some of the diagrams that I give you, the nucleus is going to be blacked in, is going to be colored in which case, just off on the side, you could write 16 protons. Somewhere on the picture, Brooke put it. But if I can put it in the nucleus, the nerd within me says, why don't I put it there? It says where they are. Is that okay? How many neutrons does it have? Well, we have to look at the mass. What's the mass of sulfur? 32. We minus the 16 protons. That tells us how many nuclei. Sorry, how many neutrons. Okay, this atom has the same number of neutrons. Oh, and you know what? I can do the little symbol. Has the same number of neutrons and protons. How many electrons does it have? Also 16. Now, later on today, we're going to talk, Brady, about how that changes and when that changes. Electrons are what we can muck around with. They're on the outer area. We can do stuff with them. That's what we do when we're doing electricity. But for now, this is a neutral atom. We're going to say it's got 16. How many? 16. So I start on the innermost shell. How many electrons can I fit on the innermost shell? How can you tell? You can memorize that. I think I gave you the 288-18 rule, or it is on your chart. In the first period, in the first row on your periodic table, how many elements are there? 2. Why? Because there's only room for 2 electrons. I usually put them right there and they pair together. How many electrons can I put in my next shell? 8. By the way, what row is sulfur in? If you count down, row 3? What that means is the first 2 shells are going to be full. It's the third shell I'm going to have to be even more careful with. So if I'm doing 8, it's going to be 1, 2, 3, 4, pair 5, pair 6, pair 7, pair 8. For a total of, how many electrons have I drawn so far? Grand total? 10. Leaving me how many? So you can do it with subtraction. The other way you can do it is if you just count from sodium, from Na, count across 1, 2. How many elements over is sulfur? Count on your periodic table.
5.
Count carefully. 6. That's the other way you can figure out how many electrons there are in the... Oh, who remembers the fancy word for outer shell? It began with the letter V. It's going to become really important. We're going to be yakking about... We called it the valence shell. So you can get there through subtracting, Alex. I've done 10. I need to do 16. I got 6 left. Or if you really want to, you can almost just glance, count across, and then fill in all the previous rows, get this one right. Which way is better? Whichever way you feel. 1, 2, 3, 4. The first 4 always go solo at north, south, east, west. How many more? 5, 6. There's going to be 2 pairs. I usually just start at the top and keep going around, so I'm going to go pair, pair. But if you wanted to, I would give you full marks if you put the extra one there and the extra one there, as long as somewhere you had 2 pairs. That is a Bohr model of sulfur. Okay? Mr. Dueck, what if we went one down further? What if we wanted to do a Bohr model of like Potassium, I would need to freehand add an extra circle or something like that. But we'll talk about that. That's kind of a review of what we were looking at. So if you want to get out the section 2.3 Bohr diagrams notes, that was this one here. We're going to go for about a half hour or so, and then I'm going to hit pause because our goal is no homework for the long weekend. We started this last class. And Mason, I would say rather than copy the stuff that you missed, follow where we're picking up and then go fill in what you missed. Don't fall behind trying to catch up. Okay? It looked like this, I think. I hope. Right? And I think we'd gotten right around to, I think we'd drawn carbon. I think we'd just about gotten to finishing touches, as a matter of fact. Okay? So y'all got it okay? I have extras. If you don't have it, tell me now, and I'll get you a copy. Yep. Need a copy? So continuing where we left off. Hopefully I'm starting to convince you. There is a lot of information on that periodic table. You don't have to memorize it, but you have to memorize how to get it. That part I can't fix. So, oh, wrong button, Mr. Dueck. Pause here. No, let's continue on. And I think I can make this a little bit bigger, Mr. Dueck, like that big. So we drew carbon, we drew chlorine. Finishing touches I wrote here. So, calculating the neutrons and filling in the nucleus. I've talked about this already a little bit, but we'll write it down in our notes formally and officially now. The atomic mass is the average mass of an atom, which is why, Nick, some of them are decimals. It turns out every atom, so every, let's say, which is one that has a decimal atomic mass, like a 35.5 pick an element. Tell me which one. Chlorine. Okay, chlorine. What's its mass? 35.5. Oh, that was a guess. Okay. Turns out now chlorine. What's its atomic number? 17. Okay. Every chlorine atom has 17 protons. It has to, otherwise it's not chlorine. What else is there in the nucleus, though? It turns out the neutrons aren't always the same, especially if elements are radioactive. You'll learn next year that radioactivity often means, in fact, we call them isotopes. An isotope simply has a different number of neutrons than the standard one. If you've heard that term before, that's where it comes from. So chlorine apparently is the fact that it's 35.5 tells you, oh, a lot of them are radioactive. A lot of them have different numbers of neutrons. The ones that work out really, really evenly or bang on, probably very few of them have a different number of neutrons. It's an average mass, for what it's worth. So mass is equal to the number of protons plus neutrons, which means if you know the mass and you know the protons, you can subtract to get to the neutrons. So the atomic mass is a decimal because the number of neutrons can vary. And again, I'll say, and the mass is just the average. By the way, what units are the masses measured in? Kilograms? No, one atom of chlorine does not weigh 35.5 kilograms. They're weighed in what we call atomic mass units, and the scale is 1 proton weighs 1 atomic mass unit. They're weighed in protons, essentially. That's what we decided to go with. So, to find the number of neutrons, you round off the atomic mass to the nearest whole number, but you round off properly. In other words, 35.5 becomes what? 36, not 35. Okay, if it's 0.5 or higher, you bump it up. If it's 0.4 or lower, you round down. And then you subtract the protons from the mass. And the answer is the number of neutrons. And this is where you can start bringing a calculator if you want, or if you're good at doing two-digit. You know what? We found most of you weren't that good at doing two-digit subtraction last class. So probably next class, a week from today, I might be, hint, 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 giving you a quiz, or else Thursday next week for sure. You probably want a calculator for that quiz, just saying. Can't use your phone. Too easy to cheat. Examples. How many neutrons are there in an atom of boron? What's boron's atomic mass? 10.8. Round it off properly, please. 11. Take away. How many protons are there in boron? 5. Boron has 6. Did I include this example in your notes or not? Yeah. I did? I don't know how you want to write that, but it's 11 take away 5. How many neutrons are there in argon? Argon's atomic mass is 39.9, which is going to be 40 minus, what's its atomic number? 18, leaving 22. Okay? So put the number of protons and neutrons either in the nucleus of a Bohr diagram, or you're going to see in some of the homework sheets that I give you, the nucleus is all blacked in. Put it beside the atom somewhere clearly. It says finish worksheet. We're going to get to that in a second. Or is that the end of your notes? That's the end of your notes? So, what makes the noble gases so stable? Why don't they combine with things? Well, first of all, the noble gases are all on the far right side of your periodic table. And what you're going to notice is each of them has a full outer shell. A full valence shell is the fancy word for outer shell. And because of that, Brooke, they don't want to react with anything. In fact, we say atoms want to have a full valence shell. By the way, atoms don't want anything because they're not living, but I'm going to pretend that they want it because it's an easy way for us to think about it. It's the laws of the universe, okay? So read along with me. It says this. Noble gases, got to go to my notes, make sure I get the right stuff. Here we go. Noble gases have full outer, what's the fancy word for outer? Begins with letter V. I'm going to put in brackets valence shells. So they can't lose or gain electrons. They're full up. All of the other atoms want a full valence shell. I put want in quotation marks because, again, atoms are dead, inanimate objects. They don't really want anything, but we're going to pretend that they're happier that way. How can they be happy? They're dead. Oh, you know what I mean. Okay? And they will lose or gain electrons to get a full shell. So think about the electron in chlorine. How can it most easily get a full outer shell? Find chlorine on your periodic table. How many electrons does it have in its valence shell? Count across from the left. How far over is chlorine? 7. It has 7 electrons in its outer shell. Now, it could either, to get a full shell, lose all 7, or what else could it do to get a full shell? Gain 1. Hey, what do you think is easier? Chlorine wants to gain 1 electron. Okay? In fact, you're going to find all of the nonmetals, they want to gain electrons to get a full valence shell. That's much easier. All of the metals, they want to lose electrons, which, by the way, is why metals are so conductive to electricity, because electricity is just moving electrons, and metals are happy to get rid of the electrons, where nonmetals would want to hang on to the electrons. They wouldn't conduct the electricity along. Come in. So we can start just by looking at the, again, if I haven't said so already, there's a lot of information on that periodic table. We can actually reason how elements are going to gain or lose electrons just based on their location. And the noble gases, because they're full already, if you really wanted them to react, you would somehow have to remove electrons from a full shell, and elements aren't happy to do that. What about calcium? Go find calcium on your periodic table. See where it is? How far over from the left is it? I'm going to ask you the same question. I want the same answer. I'm just going to phrase the question differently. How many electrons are there in its valence shell? 2. So it could either gain 16 electrons or lose 2 electrons. What do you think it's going to do? It's going to lose 2. Okay? Now, look at calcium. What number do you see in the top right corner? If it's going to lose 2 electrons, what number do you see in the top right corner? 2 plus. It's saying it's going to lose 2 negatives, 2 electrons. That ion charge, that number, comes from how many electrons this atom wants to gain or lose. If it wants to gain electrons, it'll become more negative. That's why the non-metals all have negative ion charges. See them? If it wants to lose electrons, it's going to become more positive. That's why, Brooke, the metals all have positive ion charges. I'm going to repeat myself. There's a lot of information on that periodic. There's a lot of stuff there. Okay? So what do you notice about the number of electrons lost or gained and the ion charge? Tells us a lot. It says answer these questions on your worksheet. Have patience. We're going to come to that. So most atoms, the atoms on your periodic table as written, are neutral. They have the same number of protons and electrons. Neutral atoms, though, Brooke, don't do much, and they're not happy. They want to have a full valence shell, but for them to have a full valence shell, they either need to gain electrons or lose electrons. And when that happens, we say they are ions. So an atom that has lost or gained electrons has a charge and is called an, here's our word of the day, ion. The charge that forms is shown in the upper right corner of each box. Now you may notice, if you're particularly nerdy, as you go towards the middle of the periodic table, some of those elements have more than one charge, and that's where some of the rules that I'm telling you are going to break down a little bit because it gets more complicated. But near the top and on the outside, we're good. How do we show that something has become an ion? Well, first we draw the Bohr diagram and we removing or adding, I guess I should say removing or adding the electrons as necessary if I want to be grammatically correct. The problem is if you just do that, whoever's looking at your picture might just think, oh, you forgot to finish the final row of electrons. To show that you did it deliberately, to show that you're making an ion, we put square brackets. And we indicate the charge outside the brackets in the upper right corner. Say what? Then it says, draw, oh, hey, they're good looking. I've been keeping my eye on you. Okay, fine. It says, draw a Bohr atom for an atom of, a Bohr diagram for an atom of sulfur, and then draw a Bohr diagram for an ion of sulfur. But I don't think I gave you room in your notes, did I? Oh, I gave you that handy dandy little Bohr diagrams practice sheet. So let me get that puppy out right here. Did we draw sulfur already? Okay, I'm going to really quickly do it again on this page here. What was sulfur? How many protons? 16 protons, 16 neutrons. And then it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. There's sulfur. Let's do a sulfur ion. Protons don't change. Neutrons don't change. How would sulfur become an ion? How would it get a full valence shell? Look where it is on the periodic table. What's the easiest way for it to get a full valence shell? It can either lose all 6 of these, or it can gain 2. What's easier? It's going to gain 2. By the way, you may be saying, where will it get those electrons from? From a metal nearby that was wanting to get rid of 2 electrons, or from 2 metals that each want to get rid of 1 electron. Give me 1 second here. Hang on, give me 1 second here. Just a minute. So, you ready? We go like this. You start out drawing the atom regularly. The first 2 shells are full. 1, 2, 3, 4, pair, 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 pair. It's the valence shell that we have to be careful with. Okay? Now, normally sulfur has 1, 2, 3, 4, 5, 6. What did you guys say that it wants? A full valence shell. And how will it do that? Gaining 2. I'm going to change colors just so it stands out more. There's a blue one that came from a metal somewhere. There's a blue one that came from a metal somewhere, and now it has a full valence shell. But then to show the marker that I did that on purpose, that I didn't just miscount, to show the marker or another science nerd, this is an ion, we go square brackets, and we put the ion charge in the top right corner, which I think is 2 minus, Mr. Dueck. It gained 2 negatives. It's 2 minus. And I read that right from my periodic table. Okay? That would be an ion. It would have a negative charge. In fact, it would have a charge of -2. It would be attracted to something that had a charge that was positive, and they would stick together, and now we're starting to make compounds. Now we're starting to build stuff on the periodic table. Back to our notes. Oh. So, nonmetals form, get that back, nonmetals form negative ions. Metals form, and this is a bit tricky, Mandy, because metals lose electrons, and when people hear the word lose, they think subtract, they think negative. But what's the charge on an electron, negative or positive? So I'm going to say it this way. Metals lose negatives. What does that make them? Positive. Nonmetals gain electrons, and again, kids think, oh, gain, that's plussing. It should be positive. No, no. Nonmetals gain negatives. What's that going to make their charge? More negative. But that's an easy thing to mix up if you're not concentrating, if you're in a rush. I still do that once in a while as well. It's an easy thing to mix up. So, nonmetals form negative ions, metals form positive ions, and some metals can form an ion in more than one way. See, copper, for example, or iron. Yep. We say they are multivalent. We say they are multivalent. Okay. So then it says here, draw a Bohr diagram of an aluminum atom and an aluminum ion. Below. Not below. Did I give you a handy dandy little sheet with circles on it? Hey, let's do it there. Okay? Let's do aluminum. Let's do the atom on the left side. Let's do the ion on the right side. Okay? You know what the first step is? Find aluminum on your periodic table. If you can't do that, you're in trouble. Element number what? 13? Which means what? 13 protons. Now, don't right away think 13 neutrons. We got to do some math. What's aluminum's mass? Oh, 27? And 13 protons. How many neutrons? 14. By the way, you'll notice if you want to put P plus and N0, you can. But if the nucleus is really small, as long as I see a P, I'll clue in that's protons. And as long as I see an N, I'll clue in that's neutrons. You don't have to put the charge on there if you don't want to, but you can. What row is aluminum in? What period is aluminum in? Moving down. Third? So the first two shells are full. So I can go 2 and 8. How many in its valence shell? Now, you can do it two ways, because I know it has 13 protons. When it's neutral, it also has 13 electrons. So I could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3 left. Honestly, I just tend to quickly read across. That's almost easier for me to do, because then I won't make a dumb math mistake. I'm better at counting than subtracting. So I would have read across, and I would have said, hey, aluminum is the 1, 2, third from the left. It's got 3 in its valence shell. 1, 2, 3. There's aluminum. And heck, let's even put Al. You can call me Al. Now let's do an aluminum ion. Did I say ion? Yeah? I almost always tend to do that at the beginning so I don't forget. And I'll even put the ion charge right away so I don't forget. What is the ion charge on aluminum from your periodic table? 3 what? 3 plus. All right. The first step is going to be the same. 13 protons, 14 neutrons. What row is aluminum in? Third. That I'm going to have to worry about, but the first two aren't going to change. They're still going to be full. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Now, normally aluminum has 3 electrons in the next shell. Does aluminum want to gain or lose electrons? Lose. How many? All 3. In other words, now its valence shell, its outer shell, has 0 electrons. I'm done. I'm not going to put anything in the outer shell. Okay? Now, aluminum is really positive right now. It's 3 plus. This is why it will really combine really well with some nonmetals. We can make lots of stuff with aluminum combining with a nonmetal, which is negative. That's an aluminum ion. Is that okay? Well, back to our notes. So draw it below. We did on. You can make a little note that you did it on your practice sheet or whatever, right? The electrons in the outer shell are called, what's our fancy word? Begins with the letter V. I'm going to use that like crazy. In fact, I guarantee that'll be a vocabulary word on your test for this unit. But we'll be using it so much, I think you'll have it. They're called valence electrons. And they determine if and how an atom will react. Okay? To determine the number of valence electrons, okay, just count over from the left side of the periodic table. Oh, that's a bit of a fib. This only works for the first 3 rows or so. Then it gets kind of weird. When you get to that row of 18, it doesn't quite work so much. After that, you can remember that all the families, all the members in a vertical column have the same number of valence electrons. So how many valence electrons does fluorine in the very top have? Count over from the left. 7. How many valence electrons does bromine and iodine have, even though they're further down, and you might be tempted to say 17 or no, 7. And this is where what I've told you, Kevin, those as you get bigger, the shells start to intertwine and overlap, and my rules don't work quite so well. But I'm telling you, if you look at the top one and just read down, they all have 7. Don't worry about counting when you get further down. All have 7. Valence electrons. So, how many valence, I think I put this in your notes, yeah? How many valence electrons do each of the following have? How many valence electrons does magnesium have? Sorry? 2. It wants to get rid of 2. It's a metal. How many valence electrons does boron have?
3.
Now, boron is tricky. Count from the left. It's got 3. Does it have an ion charge on your periodic table, though? Boron and carbon are kind of weird, and I'm not going to get into why that's the case. And again, like I've said a bunch of times, Danielle, a lot of the rules that I'm telling you, they're not quite rules all the time. They're going to break down, but it'll work most of the time. So boron, if you count from the left, 3. Chlorine. 7. Selenium. Now, it's in the section where stuff breaks down. It doesn't have it go above it to the one at the top of the row, right? Because selenium right here, this is where the rule breaks down. Instead, go look right here. How many does oxygen have? 6. How many does sulfur have? 6. How many does everything in that column have? 6. When you get further down, don't bother counting. Use the reference right above. How many does tin have? Where is tin? Tin is SN. Oh, there it is, right there. I'm not going to count all the way across. Instead, 4. How many does gallium have? Where is gallium? I think gallium is G or G. Oh, there it is. Right there. 3. Is that okay? Now, did I include all these questions in your notes? I don't think I did I? Did that take us to the end of that set of notes, or is there stuff on the back page? I got more? We're going to pause here.